And our next speaker is Evgenia Korobko.
Okay. Good afternoon, good morning. Thank you for invitation. Thank you for the ability to take part in this conference. And today I'm going to present you the talk about existence of a solution of discrete emden-fowler equation caused by continuous equation. This talk is based on an article that was just published in the journal Dynamic and Continuous Dynamic Systems in serial S, and it was just published in December. And three authors did it. It was by Irina Stashowa, Yezov Diblek, and me. Here we are going to present our results, and we will discuss the second order emden-fowler difference equation provided by the form of 1, where k is the set of some natural numbers. Delta is the first difference that is defined by the following formula, that it is u from k plus 1 means u from k. Delta squared is the second derivative, so it's the derivative of the first derivative, and it is also can be provided by the following formula. And here we discuss only the case of alpha and n are some real numbers, such that alpha is not equal to 0, m is not equal to 0, and unit. As you see, this equation is quite a natural generalization of the continuous emden-fowler differential equation, which was also studied in different forms, but sometimes in literature it appears in the following form: sigma and k are also some constants. This equation in classical form, in differential equations, has lots of research. As you see, the previous speaker was also telling us about qualitative theory of differential equations. And here I provide you some articles, basic articles about theory of differential equations. The main problem that if we discuss the following equation in classical form, it has the solution, the strict solution, but the difference equation doesn't have. So we are going to prove that difference case has the solution u from k such that the form 2 holds. A, B, and S are the constants that are provided by the forms of 3, 4, and 5. It is also can be mentioned that in classical case, the solution of the classical emden-fowler equation has the solution just A multiplied by k to the power of minus s, where A and S are also provided by this form. But as I also said, the difference case doesn't have this exact solution. So we are going to prove the following theorem. In our theorem, there appear some conditions on S and M, and where some system of inequalities such that if this system holds, there will exist the solution with the provided asymptotic behavior. We need to be S be greater than -1, M not equal to 0 and 1, and if we assume that there exist some positive numbers epsilon 1, epsilon 2, epsilon 3, and epsilon 4, such that either the first in a system of inequalities hold or the second one. Then, for some sufficiently large fixed k0, there will exist a solution of our difference equation such that the following inequalities on our solution will hold. B and S and A are provided by these forms. Later, I will also give you some sketch of the proof, but the proof basically is based on the following preliminaries, which was published in these articles by Joseph Diblik about asymptotic behavior solutions of discrete equations and discrete retract principle for systems of discrete equations. And it deals with the system of discrete equations of the form 6. We also put some vector function f and denote to the set of functions bi little and ci little such that bi little from k is less than ci little for each k from our natural set. Later, we will need to verify some actual functions bi big and ci big and actual sets omegas. And under these restrictions, we can show the following theorem, that if we have some continuous with respect to y functions f, and let the following two inequalities hold, the inequality of 12 and 13, that fi is less than bi from k plus 1 minus bi from k, and fi is greater than ci from k plus 1 minus ci, then there will exist a solution of our system of discrete equations such that the following inequality will hold. So we will have the estimations for our solution y. It will lie between bi little function and ci little function. This lemma gives us the idea how we can try to solve our problem in discrete case. So we will just try to transform our difference equation, emden-fowler nonlinear equation, to the system of equation using some change of variables. The change of variables is provided here in 14, 15, and 16. Also, A and B are the numbers that were mentioned previously. They were here, A, B, and S. Just we use plus minus sign in order to evaluate what of the sign of the equation it will be. And our emden-fowler difference equation transforms using this change in variables to the system of two difference equations with variables y0 and y1. Later, we will define we will need to define some functions f1, f2 and we will define them as the right-hand part of these two equations. F1 will be the right-hand part of the equation 17, and f2 will be the right-hand part of the equation 18. And we enter function bi little and ci little. Here are b1, b2, c1, c2 as 4 different constants. It is easily can be seen that bi little is less than ci little, and then later to use the lemma from preliminaries, we need to construct the following 4 inequalities that should hold whenever y1 and y0 lie between these 4 constants. Solving the following system of inequalities give us the conditions of the theorem. They are mentioned here. I wrote it again. So we get that we need system of inequalities will hold, then there will exist this solution which lies between the following inequalities as here in the theorem. The later research tells us about the problem that the formulation of the theorem deals with the variables that doesn't exist in our main equation. That means that we've entered the variable s that also has the dependence on variables alpha and m, but we want to provide the conditions only in variables alpha and m that were only in our main task, in our main equation. So later we transform the conditions from the theorem into some conditions on alpha m, and we visualize it on alpha m plane. That I will show you later. A little just below, when we will show, when I will show you the pictures, the sets that we will show there will be open, so their boundaries will not consider in these sets. When we will try to solve the first system of inequalities, this system disintegrates into different cases according to the variable m. If m is greater than 1, then our system of inequalities, after some transformations, just turns into the following picture. So we will have only the inequalities that are mentioned in the 26th number. It's the orange set. Then the other case is when m is less than 1. Then our system can be transformed into the following form, and that is equivalent to the following two possibilities, possibilities 27 and 28. That could be easily visualized on the following m alpha plane. These two pink sets. As I also said, boundaries are not considered in our picture. The second system of inequalities, it is written here in 29. It also disintegrates into two different cases. The first of case also considers about m be greater than 1. This system takes the following from 30, and it could be visualized on this picture. So we have this blue set. The second case is when m is less than 1. The system will take the form 31, and here it disintegrates into three different possibilities, into the first, second, and third possibility that could also be described on the m alpha plane in the following form. We have this green subset, this little triangle, and something like this. If we combine all the conditions, we can get this following picture. As you see, and these are the conditions for that on alpha and m that gives us the answer that the solution of our emden-fowler discrete equation will have the following asymptotic form. But also it's a good task it's a good question how to verify the conditions from other sets. Will there exist the solution with the following asymptotic form if we put the alpha and m variables from the other sets that are not mentioned in these pictures? Now some examples. The first example tells us about m and alpha that we take from the orange domain from here. We put alpha be equal to -1, m is equal to 2, and our emden-fowler type equation, discrete emden-fowler type equation, transforms into the form 33. We put variables epsilon1 and epsilon2 be equal to 1, and epsilon3 and epsilon4 be equal to 5 divided by 6. Then we also can calculate our variable s, and to verify that all the conditions of our theorem hold. If we transform the results of our theorem into some more accurate form, we'll get that function u, the solution of our emden-fowler type equation, will lie between these two functions. And here we provide a different case in case when in the equation there is plus, and in case when the equation there is minus. So we can obtain some asymptotic form of our solution u in this case. The second example tells us about the point from the green domain, from here. And here, more accurate, we take it from the green triangle. We put alpha b equal to -7/4, m is equal to 1/2, and that means that our equation transforms into the form 35. We also need to verify some constants epsilon1, epsilon2, epsilon3, and epsilon4. Here we put epsilon1 be equal to epsilon2 be equal to 1, epsilon3 is equal to epsilon4 and is equal to 1/3. And then after applying our main theorem, we can evaluate that the estimation on our function u will hold in such form. As you see here, there is no there is no difference between the sign of the emden-fowler equation. Why we studied this equation? As I previously mentioned, there are lots of works on classical quantitative theory of emden-fowler type equations, but it is we can hardly find some works about discrete case, what happens in the discrete case. The only work that we could find was by Erba, Bauer, and Peterson, and it tells us about asymptotic behavior of solutions of emden-fowler equations on time scales. I can, to talk about this article, I'll give you some just little preliminaries about timescales, what we call a timescale. Timescale is a closed non-empty subset of real numbers. And here we need to verify the timescale the timescale derivative. And to define it, we need some forward and backward operators. Sigma is a forward jump operator, rho is a backward jump operator, and the delta differential function it will be delta differentiable in some point. In two cases, we define it if a function is continuous by the classical classical difference, and if the forward jump operator is greater than t, so that means that we have something like discrete case. The definition of the delta differentiable function is provided by this form. So as you see, the theory of our discrete equations can be the part of the theory of timescale calculus. And in their article, they put they studied the equation of emden-fowler type provided by the form 37 and proved that if that there will exist a solution such that the limit of the solution divided by t is equal to some non-zero constant, provided then the non-linear part is just sufficiently small. So when we have this integral, when this integral converges, the integral also is in time scale calculus. So that means that it's not a natural integral as in normal calculus. We also can transform these results in terms of difference equations. They are the integral transformed into some sum. So we need to show that if some sum converges, then the equation, the emden-fowler discrete emden type equation, will have a solution such this limit will hold. And how our results can be combined with this result. As we have seen in the first and second example, for example, in the first example, we've entered the emden-fowler type equation. We can show that this equation has the following asymptotic formula. And if we try to check the result from the timescale calculus, that means that in our case, the following sum diverges, so that theorem can be applied for this equation, but we get the same asymptotic behavior of the solution as in that theorem. The other case from the example 2 gives us the following asymptotic formula. It is different from the form of the result of Peterson, Bauer, and Erba, but the sum, so that means that their the sum that we need to check converged or diverged, it converged. So that means that condition also can give us the other asymptotic behavior of solution of the following discrete emden-fowler type equation. For further investigations, we also want to expand the set of applicable alphas and m's that are described in this picture, and we also made some further steps. So if we change these functions, if we put, for example, on the left-hand part and on the right-hand part, not constant functions, but functions of the form minus epsilon divided by k to the power of gamma, where gamma lies between 0 and 1, that means that we found some extra sets where this where there will be the same asymptotic, not the same, some power type asymptotic of our Lane emden-Fowler equation. So that is the article that under what the speech was based, and thank you for your attention.
Okay, thank you very much. And what questions do you have? No questions, as I can see. I would like to ask you, for example, if we will consider the case of time scale equation, you would like to obtain, for example, also the domains of parameters where we have such type of solutions, yes?
Maybe, yes, I think.
For further thinking.
Yes, but we still don't cover the time scale calculus. We just take only the difference case. Also, the other transformation of our equation, as I mentioned in the beginning, we used the definition of the first difference in the following form. Yes, but as you know, we also can put some h function. We can here we're just stepping by the discrete scale where where is only unit between 2 points, but we can transform it into the some h distance between two first points, and try to evaluate whether our result transformed into, if we tense h to the zero, or whether our result transforms into the classical differential case. Maybe all the sets will transform into the whole set, and as we know that in the classical result there exists a solution, the exact solution. We also hope that if we do something like this, all our cells would transform to the whole real set of applicable alphas and m, and it will also hold, and we'll find the asymptotic behavior.
Okay, we hope. Thank you very much.